There is more structure in the night sky than light can reveal. Every star you can see belongs to a galaxy, and every galaxy rests within a larger gravitational landscape. The bright spirals, pale ellipses, and scattered clusters recorded by telescopes are not floating freely through empty space. Their motions suggest that they are held inside something broader, heavier, and unseen. Astronomers call it dark matter. The name can sound as though it describes a shadow or a substance hidden behind the stars. But dark matter is not dark in the ordinary sense. It does not appear black against the sky. As far as scientists can determine, it does not emit, absorb, or reflect enough light to be observed directly. No telescope has taken a simple portrait of it. Its presence is known through gravity. A galaxy turns, and the stars near its outer edge move faster than the visible matter alone should allow. A cluster of galaxies bends the light of objects far behind it, producing arcs and stretched images whose shapes reveal more mass than the cluster's glowing stars and gas can provide. Across billions of light years, galaxies gather along filaments and around dense intersections, tracing a cosmic web that seems to have grown around an invisible framework. This web is not a single object suspended in space. It is a pattern formed over cosmic time, as gravity drew matter toward regions that began slightly denser than their surroundings. Galaxies gathered where those regions deepened. Clusters formed at the busiest crossings between them. Immense stretches became comparatively empty. The visible universe still carries this underlying pattern in the places where its galaxies appear. What we see is the illuminated part of a much larger design. All the familiar matter in stars, planets, oceans, dust, and living cells forms only a small share of the universe's total contents. Dark matter is thought to account for about 5/6 of all matter. Yet its physical identity remains unknown. It may consist of particles not yet included in our present description of nature. It may require an idea that has not been fully imagined. For now, scientists can map where its gravity gathers without knowing what the substance itself is made of. That is the unusual balance at the center of this story. Dark matter is hidden, but its influence is not vague. It can be measured in the speeds of stars, in the paths of galaxies, in the bending of distant light, and in faint patterns left from the early universe. Different observations made with different instruments and across different scales point toward the same missing mass. This episode will move through those scales. We will begin inside galaxies, where some of the clearest clues emerged in motions that did not match the matter astronomers could see. From there, the view will widen to galaxy clusters, where gravity turns space into a lens. Beyond the clusters lies the cosmic web, a structure of filaments, knots, and broad empty regions extending across the observable universe. And beneath all of it remains the unresolved question of what dark matter might be. The journey does not require us to picture an invisible object, as though it were merely waiting for better lighting. Dark matter does not appear to gather into stars, clouds, or solid surfaces the way ordinary matter does. Its architecture is known through relationships. How one body moves around another, how light changes direction, how matter gathers over time. So the universe we enter tonight is not missing its structure. The structure is already there. We are learning to read it without seeing it. For a long time, a galaxy could be studied mostly by the light it offered. Astronomers photographed its spiral arms, measured the color of its stars, and estimated how much luminous material was gathered near the center. The picture seemed complete enough. A bright central bulge, a flattened disk, lanes of dust, and a faint outer edge where the starlight thinned into the background sky. But a galaxy is not only an image, it is a moving system. Stars circle the center. Clouds of hydrogen travel through the disk. The speed of that motion carries information about gravity, because orbital motion depends on the mass enclosed within an orbit. In the solar system, most of the mass lies inside the Sun. Farther planets, therefore, move more slowly than nearer ones. Earth travels around the Sun faster than Saturn, and Saturn faster than Neptune. If the visible mass of a spiral galaxy were concentrated mainly in its bright inner regions, something similar should happen. Beyond most of the starlight, orbital speeds should rise near the center, reach a maximum, and then gradually fall as the distance increases. That expected decline became one of the most important missing features in modern astronomy. To measure the motion of a distant galaxy, astronomers do not watch individual stars complete their orbits. One galactic year can last hundreds of millions of years. Instead, they divide the galaxy's light into a spectrum and look for small changes in wavelength. Light from material moving toward Earth shifts slightly toward the blue. Light from material moving away shifts toward the red. One side of a rotating disk approaches while the other recedes. By measuring those shifts at many positions, astronomers construct a rotation curve, a simple graph showing orbital speed at increasing distance from the galactic center. The inner parts often behave much as visible matter predicts. Speeds rise as more of the galaxy's stars and gas are enclosed. Farther out, however, the curve commonly refuses to descend in the expected way. It remains nearly level across regions where the visible disk has become thin. This means that stars and gas near the outskirts are still moving rapidly. If only the observed material were present, some of those outer orbits would not fit the gravitational field inferred from the light. The galaxy would appear to contain too little mass for the motion it sustains. During the 20th century, many observers helped bring this discrepancy into focus. Optical measurements traced the motion of glowing gas in spiral galaxies. Radio astronomy then extended the view by detecting the 21-centimeter signal from neutral hydrogen, which often reaches far beyond the bright stellar disk. Those outer hydrogen clouds became useful test particles. They were faint in visible light, but their radio emission allowed astronomers to follow galactic rotation into regions where most of the stars had already disappeared from view. In the 1970s and early 1980s, measurements by Vera Rubin, Kent Ford, Norbert Tonnerd and other teams showed that the pattern was not a peculiarity of one unusual galaxy. Across many spiral systems, rotation remained unexpectedly strong at large radii. The exact shape varied from galaxy to galaxy, but the broad message endured. The gravitational mass did not fade away as quickly as the visible light. One way to make sense of this is to place the luminous galaxy inside a larger halo of unseen matter. The word halo can be misleading if it brings to mind a bright ring. A dark matter halo would not be a surface or a narrow shell. It would be an extended, roughly rounded distribution surrounding and passing through the visible galaxy. The stellar disk would occupy only the bright inner region of a much broader gravitational structure. Near the center, stars and gas can provide a large share of the gravitational pull. Farther out, where luminous matter becomes sparse, the halo's contribution grows more important. The combined mass can keep orbital speeds from dropping as sharply as a light only model predicts. This does not mean every galaxy has the same halo. Large spirals, small dwarfs, diffuse galaxies, and elliptical systems all carry different histories and internal motions. Gas may not always follow perfect circular paths. Bars and spiral arms can disturb the flow. Stellar mass must be estimated from light, and that estimate depends on the ages and compositions of the stars. A rotation curve is therefore not a photograph of dark matter. It is an inference assembled from motion, distance, geometry, and models of visible mass. In smaller galaxies especially, non-circular motion and temporary disturbances can complicate the reconstruction of the underlying gravitational field. Even so, the pattern is difficult to dismiss. The discrepancy appears across many nearby galaxies, measured with different instruments and different tracers. The farther the observations extend beyond the main stellar disk, the clearer the need often becomes for additional gravity. There is an important distinction here. Rotation curves reveal a problem of missing mass, or perhaps missing physics. By themselves, they do not prove what dark matter is made of. They do not identify a particle. They show that the gravity inferred from galactic motion exceeds what the observed stars and gas readily explain under the usual laws of gravity. Some researchers have explored whether gravity itself might behave differently at the very low accelerations found in galactic outskirts. Those ideas can reproduce parts of the rotation curve pattern and remain subjects of scientific testing. Any successful explanation, however, must also account for galaxy clusters, gravitational lensing, the growth of cosmic structure, and the early universe. The halo model connects naturally with that wider evidence, which is why dark matter became more than a local adjustment to spiral galaxies. It offered a common invisible component that could act across many scales. For now, the view can remain close to one galactic disk. Imagine moving outward from its bright center. The density of stars falls. Spiral arms become less defined. The familiar glow weakens until only scattered stars and cold hydrogen remain. Yet, the orbital motion does not lose strength as quickly as the light. The visible galaxy is ending, but its gravitational reach continues. Long before astronomers could map the cosmic web, they found its first nearby suggestion in this mismatch between brightness and motion. The stars traced one boundary, gravity traced another, and the larger boundary could not be seen. Beyond the edge of a single galaxy, the same unseen influence appears on a larger scale. Galaxies do not usually stand alone. Many gather into groups, while hundreds or even thousands can belong to enormous clusters held together by gravity. Between them lies hot gas, spread through space so thinly that it would feel almost empty, yet occupying a volume far larger than the galaxies themselves. A cluster can span millions of light years. At first glance, most of its visible material seems to be divided among the galaxies. Each one contains stars, dust, stellar remnants, planets, and clouds of gas. Yet, when astronomers measure how these galaxies move through the cluster, the visible matter again seems insufficient. The first major clue came before galaxy rotation curves were widely studied. In the early 1930s, the astronomer Fritz Zwicky examined the Coma cluster, a rich gathering of galaxies in the northern sky. He measured the speeds at which its members were moving toward or away from Earth. Those speeds were remarkably high. A gravitationally bound cluster is a little like a swarm in constant motion. Its galaxies travel in different directions, but the collective gravity of the system prevents them from escaping. If the mass is too low, the fastest should drift away, and the cluster should gradually disperse. Zwicky estimated how much visible matter the Coma cluster contained, then compared that value with the gravity required to hold its rapidly moving galaxies together. The difference was large. The luminous material accounted for only a fraction of the needed mass. He described the missing component with a German phrase meaning dark matter. At the time, the conclusion was difficult to evaluate. Distances to galaxies were uncertain. Their true luminosities were not well known. Astronomers had only a limited understanding of how clusters formed or evolved. Even the scale of the universe was still being revised. Yet the central problem remained. As observations improved, galaxy clusters continued to behave as though they were far heavier than their stars could explain. Their galaxies moved too quickly. Their hot gas reached temperatures that required deep gravitational wells. Light passing through them bent more strongly than the visible material alone predicted. These are three different kinds of evidence, and each reads the cluster in a different way. The motion of galaxies traces gravity through orbit and speed. The temperature of gas traces gravity through heat. Gravitational lensing traces gravity through the path of light. Together, they allow astronomers to examine a cluster without depending on a single measurement. The hot gas is especially important. Space between cluster galaxies is not truly empty. It contains an immense atmosphere called the intracluster medium. This gas has been heated to millions of degrees as matter fell into the cluster's gravitational field and as smaller systems collided and merged. At those temperatures, the gas shines mainly in X-rays rather than visible light. X-ray telescopes reveal clouds extending throughout the cluster, often concentrated around its central region. In many clusters, this hot gas contains more ordinary matter than all the stars in all the member galaxies combined. That finding closes part of the early gap. The stars were never the whole visible story. A great deal of normal matter was hiding not because it was dark matter, but because human eyes could not see the wavelength in which it glowed. Even after the gas is included, however, most of the required mass remains unaccounted for. The gas is hot because particles move rapidly. To keep such energetic material from escaping, the cluster must possess a powerful gravitational field. Astronomers can measure how temperature and density change from one region to another, then calculate the mass needed to keep the gas in place. The answer is again much larger than the combined mass of stars and gas. This larger gravitational structure is often described as a cluster-scale dark matter halo. It surrounds the galaxies and extends through the intracluster medium, shaping the entire system. But gravity offers another method, one that does not require galaxies or gas to be in a settled state. A massive object changes the geometry of space-time around it. Light traveling near that mass follows the curved geometry and appears to bend. A galaxy cluster can therefore act as a natural lens, redirecting light from objects far behind it. The effect was predicted through general relativity, and it turns clusters into immense optical instruments created by gravity itself. Sometimes the result is dramatic enough to see directly in astronomical images. A distant background galaxy may appear as a long arc wrapped around the cluster. In rare alignments, several distorted copies of the same galaxy can appear at different positions. A nearly perfect alignment may produce a ring. These shapes are not physical structures stretching through space. They are altered images, produced as light follows different curved paths around the foreground mass. The amount and pattern of distortion depend on how that mass is distributed. By studying many arcs and repeated images, astronomers can construct a map of the cluster's gravitational field. This technique is known as strong gravitational lensing. Farther from the center, where the bending is weaker, background galaxies are not transformed into obvious arcs. Their shapes are altered only slightly. Any one galaxy may already be naturally elongated, so the effect cannot be recognized from a single image. Across thousands of background galaxies, however, a statistical pattern appears. Their orientations show a small shared distortion caused by the foreground cluster. This is weak gravitational lensing. It allows mass to be mapped across a broad region, including places where little visible matter is present. The resulting map can then be compared with the locations of stars, galaxies, and X-ray emitting gas. Again, the gravitational mass extends beyond the luminous material. Lensing has a particular advantage. Gravity bends light regardless of whether the source of that gravity is bright, dark, hot, cold, or invisible to ordinary telescopes. The lens responds to total mass. This does not make the reconstruction simple. Astronomers must know the approximate distances of background galaxies, account for telescope effects, estimate their undistorted shapes, and model the geometry of the cluster. Different mass distributions can sometimes create similar lensing patterns, yet with enough background sources and carefully measured arcs, the hidden structure becomes increasingly constrained. In some clusters, this structure appears relatively smooth. In others, it is divided into smaller concentrations associated with individual galaxies or groups. These details carry traces of the cluster's formation history. Clusters grow through collisions. They assemble as smaller groups fall together along the filaments of the cosmic web. Galaxies pass through one another with little direct contact because the distances between stars are so large. The clouds of hot gas behave differently. They collide, compress, heat further, and slow down. This separation becomes especially useful in systems observed during or after a major merger. One well-known example is the Bullet Cluster, a pair of galaxy clusters that have passed through each other. X-ray observations show that much of the ordinary matter in the form of hot gas was slowed by the collision and left between the outward-moving groups of galaxies. Gravitational lensing maps place the largest concentrations of total mass closer to the galaxies than to the central gas. The pattern suggests that most of the mass passed through the collision with relatively little resistance, while the ordinary gas interacted strongly and lagged behind. Within the standard dark matter model, this is what would be expected from a component that responds mainly through gravity and rarely collides with itself or ordinary matter. The Bullet Cluster is not a simple portrait of dark matter, and no single cluster settles every question. Its geometry must be reconstructed from a brief stage in a collision that has unfolded over immense timescales. Other merging clusters show different alignments and complexities. Still, such systems offer something that an undisturbed cluster cannot. They separate the major forms of matter, allowing their behavior to be compared. The stars move with the galaxies, the gas slows and heats. Most of the gravity follows a path closer to the galaxies than to the gas. A cluster merger is therefore more than a collision of visible objects. It is a temporary experiment in which the universe sorts its components according to how they interact. The scale of this process can be difficult to hold in the mind. Each point of light may contain billions of stars. The gap between neighboring galaxies can stretch for hundreds of thousands of light years. The entire merger may take more than 1 billion years to unfold, yet from Earth, the cluster may occupy only a small patch of sky. A telescope collects X-rays from the gas. Another records the colors and positions of galaxies. Deep images reveal faint background arcs. Computers combine these layers into a reconstruction of mass that no instrument can photograph directly. The hidden architecture becomes visible only through its effects on other things. At the scale of galaxies, dark matter was inferred from motion that stayed strong beyond the light. At the scale of clusters, the evidence becomes more varied. Galaxies move within a common gravitational well. Hot gas reveals the depth of that well. Distant light is curved as it passes through. 3 paths lead toward the same conclusion. The cluster contains more gravity than its ordinary matter can provide. And once that pattern appears across many clusters, the question begins to widen again. These systems are not scattered randomly through space. They gather at particular locations connected by structures far larger than any single cluster. The invisible halos around galaxies are only the smaller rooms. Beyond them lies the framework of the universe itself. The wider pattern begins long before any galaxy exists. To understand why matter forms a web instead of spreading evenly through space, the view has to move back toward the early universe, when there were no stars, no planets, and no clusters. Space was filled with a hot mixture of particles and radiation. It was remarkably uniform, but not perfectly so. Some regions contained slightly more matter than others. The differences were small. In maps of the cosmic microwave background, the relic light released. The universe was about 380,000 years old. They appear as faint variations in temperature. These variations record tiny changes in density. The warmer and cooler patches do not show galaxies already formed. They show the early conditions from which galaxies would eventually grow. Gravity had very little to work with, but it did not need much. A region with a little more matter exerted a little more gravitational pull. Nearby material responded by moving toward it. As the region gained mass, its attraction became stronger, allowing it to gather still more. A slight imbalance could therefore deepen over time. The process was not fast. The universe was expanding, carrying matter apart. Even as gravity drew it together, structure emerged through the competition between those two motions. Expansion increased the distances between large regions. Gravity amplified local differences within them. Dark matter played a central role because it did not behave like ordinary matter in the early universe. Ordinary matter was then mostly a plasma of electrically charged particles. Light scattered repeatedly from those particles, pressing against them and preventing them from settling easily into growing gravitational concentrations. Matter and radiations moved as a coupled fluid, producing waves whose traces remain in the cosmic microwave background. Dark matter, as the standard model describes it, did not interact strongly with light. It could pass through the radiation without being carried along by the same pressure. Its small density variations began developing into a hidden gravitational pattern, while ordinary matter was still tied to the bright, hot plasma. When the universe cooled enough for electrons and atomic nuclei to combine, light could finally travel freely. The relic radiation began its long journey through space, and ordinary matter was released from its close partnership with light. By then, the dark matter landscape had already begun to form. Gas fell toward its denser regions. It collected inside gravitational wells that had no luminous surface and no sharp boundary. Over time, some of that gas cooled, contracted, and formed the first generations of stars. Those stars gathered into young galaxies within dark matter halos. The visible universe began lighting up inside an architecture that gravity had been preparing in advance. This architecture was never expected to be a simple field of evenly spaced spheres. Gravity acts in 3 dimensions, and the original density pattern contained structures at many scales. Matter flowed first, away from regions that were slightly emptier. It collapsed more quickly along one direction, forming broad sheets. Further collapse along another direction produced filaments. Where several filaments met, matter accumulated into dense nodes. Inside those nodes, galaxy groups and clusters grew. Between them, the underdense regions expanded and became cosmic voids. A void is not a perfect vacuum. It may contain thin gas, dark matter, and small galaxies. It is defined by comparison with the crowded filaments and clusters around it. Matter has gradually moved away from its interior, leaving a broad region with far fewer galaxies. The result is the cosmic web. Its filaments can extend for tens or hundreds of millions of light years. Some are thick bridges connecting massive clusters. Others are faint strands carrying smaller galaxies and diffuse gas. Sheets form broader boundaries around the voids. Nodes mark the intersections where the strongest concentrations gather. A map of galaxies traces this pattern, but galaxies do not contain all of it. They are the luminous markers placed within a much larger distribution of dark matter and gas. There is no single center to the web. It does not radiate outward from one location, and it was not assembled around a central object. The pattern exists throughout the observable universe, changing from region to region, according to the original density field and the long history of gravitational growth. If you could step far enough back from the galaxies, the arrangement might resemble a network of strands surrounding empty cells. But the familiar image of a web is only an analogy. Cosmic filaments do not hang in a flat plane. They curve, branch, overlap, and pass through 3-dimensional space. A cluster may sit at a junction connected to several structures extending in different directions. The full geometry is difficult to represent on a page or screen. Astronomers often rotate computer models or move through them virtually, because any single view compresses depth into a flat image. These models begin with conditions based on measurements of the early universe. Scientists fill a simulated volume with matter, give it the small initial variations supported by observations, and allow gravity and expansion to shape it over billions of years. At first, the distribution appears nearly smooth, then fine threads emerge. Small concentrations form, merge, and gather along larger filaments. Halos grow around galaxies. Groups fall toward clusters. Voids widen as matter drains toward their boundaries. By the present era, the simulation has developed a complex network resembling the large-scale distribution measured by galaxy surveys. This resemblance is one of the strongest achievements of the dark matter model. It does not begin with the web already drawn in. The web grows from early conditions through known gravitational behavior, with dark matter providing most of the mass that guides the formation. The word cold is often added to the model, producing the phrase cold dark matter. Here, cold does not mainly describe temperature. It means the dark matter particles were moving slowly enough relative to the expansion and the scales involved that small structures were not erased by rapid motion. In this picture, smaller dark matter halos form first and combine into larger ones. Galaxies grow through gas accretion, star formation, and mergers inside that evolving hierarchy. Clusters appear later, assembled from many earlier systems arriving along filaments. Different possible forms of dark matter could alter this sequence. If the particles moved faster in the early universe, they could smooth away structure below a certain scale. If dark matter interacted with itself more strongly, the inner shapes of halos might change. If it behaved like an extremely light wave, interference could leave another kind of pattern. The cosmic web is therefore not only evidence that unseen mass exists, its details may contain clues about what that mass can and cannot be. Large-scale structure is measured in several ways. Astronomers record the positions and distances of enormous numbers of galaxies. They study how often galaxies appear separated by particular distances. They examine the distortion of background light by weak gravitational lensing. They map hydrogen gas through absorption lines in the spectra of remote quasars. Each method reveals a different part of the network. Galaxy surveys show where luminous systems gather. Lensing responds to the total mass along the line of sight. Quasar light can reveal gas too faint to glow on its own, including material spread between galaxies along filaments. No single map displays the complete web without interpretation. Distance measurements carry uncertainty. Galaxies are biased tracers, forming more readily in some environments than others. Lensing compresses three-dimensional matter along the viewing direction. Simulations depend on assumptions about cosmology and particle behavior. Yet the larger pattern appears again and again. It is present in the distribution of nearby galaxies. It appears in maps reaching billions of light years into the past. It emerges in numerical universes built from the early density fluctuations, and it connects naturally with the halos inferred around galaxies and clusters. The same dark matter that helps hold stars in wide galactic orbits also participates in structures spanning a significant portion of the observable cosmos. The web is still evolving. Matter has not reached a final arrangement. Galaxies continue to move within groups. Groups approach larger concentrations, and clusters gain material from their surroundings. Simulations and observations suggest that filaments help guide this growth, channeling galaxies and gas toward denser intersections. The motion is not a smooth current, with every object traveling in one direction. Orbits cross, systems merge, and local gravitational fields complicate the flow. Even a cluster that appears settled can be receiving smaller groups along several connected filaments. Their arrival may stir its hot gas, reshape its dark matter distribution, and leave streams of galaxies that have not yet mixed with the older population. This continuing assembly explains why the web contains both order and irregularity. Its broad form follows gravity across cosmic time, while each region carries the details of its own collisions, near passages, and periods of growth. The architecture is stable enough to recognize, but never frozen. For a listener resting beneath an ordinary ceiling, that scale may seem remote from the present moment, but the matter in the room, the planet below it, and the galaxy surrounding both are all located within this larger terrain. The Milky Way belongs to a small group of galaxies. That group lies within a broader region shaped by nearby filaments, voids, and clusters. There is no physical strand passing through the room like a cord. The connection is gravitational and historical. The local universe formed where it did because matter flowed through a pattern established long before the sun existed. Our galaxy did not choose an empty coordinate in space and begin alone. It grew inside a halo. That halo developed within a filamentary environment, and the filament emerged from density differences written into the early universe. Seen in this way, the cosmic web is not a distant layer added beyond galaxies. It is the context that allowed galaxies to become what they are. Stars illuminate selected places within it, but the deep pattern is carried mostly by matter that gives off no light. The web was there before the first star began to shine. Its faintest outlines were already present in the oldest light we can observe. The web can be mapped through gravity, but a map does not reveal what the unseen material is. It tells astronomers where additional mass must be gathered. It shows that the hidden component surrounds galaxies, deepens the wells of clusters, and guides matter into filaments. Yet gravity alone does not say whether that component is one kind of particle, several kinds, or something more compact and unexpected. So the question narrows. What can dark matter be made of? Whatever the answer is, it must satisfy several conditions at once. It must carry mass. It must remain stable, or at least survive for times comparable to the age of the universe. It must interact with light so weakly that it does not form luminous clouds, absorb starlight, or announce itself through ordinary radiation. And on large scales, it must move slowly enough in the early universe to allow structures to grow rather than washing them away. These conditions leave room for many possibilities, but they also remove many familiar ones. Dark matter cannot be explained mainly by dim stars, cold planets, or ordinary dust. Those objects are made from the same protons and neutrons as visible matter, and the abundance of those particles is constrained by elements formed in the early universe and by patterns in the cosmic microwave background. Black holes formed from collapsing stars are ordinary matter too, and their total population cannot supply the full missing mass. There is still scientific interest in primordial black holes, which might have formed from dense regions in the early universe before stars existed. Depending on their masses, they could behave as a dark component. But searches using gravitational lensing, cosmic radiation, stellar motion, and other effects have restricted much of the possible range. They remain a candidate in limited regions, not a settled explanation for all dark matter. Most searches, therefore, look beyond the known inventory of matter. One long-standing idea is a weakly interacting massive particle, usually shortened to WHIM. The name describes a broad class rather than one precisely defined particle. A WHIM would have mass, would respond to gravity, and might interact through a force weaker than electromagnetism. It could pass through ordinary matter almost all the time, while only rarely colliding with an atomic nucleus. If such particles form the Milky Way's halo, then the solar system should be moving through an unseen population of them. Earth turns around the sun while the sun travels through the galaxy, carrying every laboratory ocean, mountain, and sleeping room through that halo. The imagined flow is not a wind-made air. Nothing presses against the skin. The particles, if they exist, would cross the planet with little resistance. Trillions might pass through ordinary material without leaving a measurable trace. A detector must wait for the rare event in which one transfers a small amount of energy to an atom. This is why many direct searches are built deep underground. Layers of rock reduce the constant rain of cosmic rays reaching Earth's surface. The detector materials are chosen for low radioactivity. Water tanks, neutron vetoes, and careful shielding help identify ordinary particles that could imitate the desired signal. The experiment is not hidden underground because dark matter prefers depth. It is placed there because the known universe is noisy. No single detector material responds equally well to every possible mass and interaction. Xenon is valuable because it is dense and can be purified, while other searchers use argon, germanium, silicon, crystals, superheated liquids, or carefully controlled electronic systems. A lighter dark particle may transfer too little energy to move a heavy nucleus detectably. A heavier one may be easier to notice through nuclear recoil, but rarer in number. By changing the target and lowering the energy threshold, experiments explore different regions of the same unknown landscape. Researchers also study how a real galactic signal might vary with direction or season as Earth changes its motion around the Sun. Such patterns would not replace the need for background control, but they could help distinguish a population connected to the Milky Way from radioactivity inside the apparatus. Inside some of the largest detectors, several tons of liquid xenon are kept extremely pure. A particle striking a xenon nucleus can produce a tiny flash of light and free a small number of electrons. Electric fields move those electrons through the detector, creating a second signal. The timing and position of both flashes help researchers determine where the event occurred and whether it resembles a nuclear collision or a more common background. The expected signal may be only a small collection of events among many years of data. Every background must be measured. Radioactive atoms can decay, neutrons can scatter, neutrinos from the Sun can strike nuclei in ways that resemble the recoil expected from some forms of dark matter. Recent results from the Lux Zeppelin and Xenon T experiments have not produced a confirmed WHIMP detection. Instead, they have placed tighter limits on how often WHIMPs of particular masses could interact with ordinary matter. These null results do not remove the entire WHIMP idea. They exclude sections of the possible landscape and force models toward weaker interactions, different masses, or different assumptions. The growing role of neutrinos marks an important change. For many years, neutrinos were among the backgrounds researchers hoped merely to avoid. Now, detectors have become sensitive enough to measure some of the nuclear recoils produced by solar neutrinos. These events are scientifically valuable in their own right, but they also create what researchers call the neutrino fog, a region where dark matter signals can become difficult to distinguish statistically from neutrino interactions. This is not an absolute wall. Directional information, larger exposures, multiple target materials, and improved knowledge of neutrino sources may help separate the patterns. But the challenge shows how far the experiments have advanced. They are beginning to encounter particles that pass through nearly everything as part of the background to an even more elusive search. Another candidate occupies a very different scale. AX. The axion would be far lighter than a typical WHIMP. It was first proposed to solve a puzzle in the theory of the strong nuclear interaction, then recognized as a possible form of dark matter. If produced under the right conditions in the early universe, an enormous number of axions could behave collectively as a cold, gravitationally influential field. An axion detector, therefore, does not usually wait for a heavy particle. to strike a nucleus. Experiments such as the Axion dark matter experiment place a resonant microwave cavity inside a strong magnetic field. Under the Axion hypothesis, the magnetic field could allow a small fraction of nearby axions to convert into microwave photons. The cavity is tuned through narrow frequency ranges, much like a receiver, searching for a station whose frequency is unknown. The expected signal is exceptionally faint. Thermal motion in the apparatus can overwhelm it, so the cavity and amplifiers are cooled and designed to add as little noise as possible. The search proceeds frequency by frequency, because the axion's mass would determine the frequency at which the conversion appears. Recent ADMX searches have examined new frequency ranges without finding a confirmed axion signal, excluding particular combinations of axion mass and interaction strength. Here again, a non-detection is not empty. It marks a region where the particle cannot hide under the assumptions being tested. WHIMPs and axions are only two families among many. Other proposals include sterile neutrinos, photons, ultralight fields, and particles that interact through forces confined mostly to a hidden sector. Some models contain more than one dark particle, just as ordinary matter contains electrons, quarks, neutrinos, and many composite forms. The word matter may be describing an entire unseen sector rather than a single missing ingredient. This wider possibility changes the meaning of the search. A detector designed for heavy nuclear recoils may be nearly blind to an ultralight field. A microwave cavity tuned for axions may not respond to a massive particle crossing liquid xenon. A collider may create unstable particles connected to dark matter without producing the cosmological dark matter itself. A gamma-ray telescope may look for products of dark matter annihilation or decay, while a gravitational survey tests how the hidden component gathers over billions of years. Each method listens for a different consequence. Direct detection looks for dark matter arriving in a laboratory. Indirect detection looks for radiation or known particles that dark matter might produce in space. Collider experiments look for missing energy and momentum in high-energy collisions, possible signs that an unseen particle carried energy away. Astronomical observations test the mass distribution and behavior of dark matter through gravity. A convincing discovery would become stronger if several of these approaches pointed toward the same properties. A laboratory recoil, for example, would need to survive background tests and repeat with the expected pattern. It would become more persuasive if collider measurements or astronomical signals supported a particle with compatible mass and interactions. The absence of such agreement is one reason scientists remain careful. Dark matter has been detected gravitationally in the sense that its effects are repeatedly measured, but no specific particle has been identified as the source. Those are two different statements, and preserving the space between them is part of scientific accuracy. There is patience built into this work. A detector may operate for years to study a handful of candidate events. An apparent excess may fade. As a background is understood more completely, a promising model may lose much of its parameter space without disappearing altogether. New instruments are then designed not simply to become larger, but to listen in a different way. The search is a movement from architecture towards substance. Galaxies show where the hidden mass acts. Clusters show how much of it gathers. The early universe shows the role it played in forming structure. Laboratories ask what, if anything, can cross the narrow boundary between that invisible population and the atoms of a detector. For now, the boundary remains almost perfectly sealed, but every carefully measured silence makes its shape a little clearer. A boundary that remains sealed invites a second question. What if the missing influence is not a new substance at all? What if the laws used to translate motion into mass begin to change in the weakest gravitational fields? This possibility is not outside the habits of science. Gravity has been revised before. Newton's description explained falling bodies, planetary orbits, and the tides with a precision that transformed astronomy. Centuries later, Einstein showed that gravity could be understood more deeply as the curvature of space-time. Newton's equations did not become useless. They became an approximation that works extremely well under familiar conditions. So when galaxies move in ways that visible matter does not explain, it is reasonable to test both sides of the equation. There may be unseen mass, or the relation between mass, acceleration, and gravity may differ from the one measured in the solar system. In the early 1980s, physicist Mordechai Milgrom proposed an approach now known as modified Newtonian dynamics, or MOND. The proposal begins with a characteristic acceleration. Above that scale, motion follows the familiar Newtonian expectation. Far below it, the effective relation changes. The important word is acceleration, not distance. A star may be far from a galactic center, but what matters in this framework is the weakness of the gravitational acceleration acting upon it. In that low acceleration regime, orbital speeds can remain nearly flat without surrounding the galaxy with a conventional halo of dark matter. MOND also connects the outer rotation speed of a galaxy with the total amount of ordinary matter it contains. This relationship resembles the observed baryonic Tully-Fisher relation, in which the mass of stars and gas is closely linked to a galaxy's characteristic rotation speed. Another pattern, known as the radial acceleration relation, compares the acceleration inferred from galactic motion with the acceleration expected from visible matter. Across many galaxies, the two are tightly correlated. Where the visible matter predicts strong acceleration, the discrepancy is small. Where it predicts weak acceleration, the discrepancy grows in an orderly way. For supporters of modified dynamics, this regularity suggests that galaxies may be pointing toward a new law. For supporters of dark matter, it may reveal a deep connection between ordinary matter and the halos in which galaxies form. Gas cools, stars appear, supernovae reshape the inner galaxy, and the dark halo responds. A complicated history could still produce a close relation between what shines and what does not. The same observation can therefore carry two interpretations. One says the visible matter determines motion through a modified rule of gravity. The other says visible and dark matter become linked through billions of years of formation and feedback. Galaxies alone have not settled the choice. MOND is highly effective as a description of many rotating galaxies, but it encounters greater difficulty on larger scales. Galaxy clusters still appear to require additional unseen mass, even after the modified relation is applied. Gravitational lensing must be explained by a theory that determines how space-time affects light, not only how stars orbit. The cosmic microwave background and the growth of the cosmic web also demand a consistent account of the early universe. Several relativistic theories have been to extend modified gravity beyond the original galactic rule. They remain active areas of research. None has yet replaced the standard cosmological model across the full range of observations. Dark matter, however, carries its own unresolved questions. On the largest scales, cold dark matter performs remarkably well. It helps reproduce the broad cosmic web, the distribution of galaxy clusters, and important patterns in the relic radiation. When simulations follow only gravity down to the scale of dwarf galaxies, the agreement becomes less simple. A cold, nearly collisionless dark matter halo tends to grow denser toward its center. In idealized simulations, the density rises into what astronomers call a cusp. Some dwarf and low surface brightness galaxies appear instead to favor a core, a central region where the density changes more gradually. This is the cusp core problem. The words describe mathematical profiles, but the measurement comes from motion. Astronomers study how gas or stars orbit near the center of a small galaxy. From those speeds, they infer how mass is distributed. A gradual rise in orbital speed can suggest a broad core. A steeper rise may be compatible with a cusp. The inference is delicate. Dwarf galaxies are faint, their gas may be disturbed, and their stars do not all travel in circular orbits. Viewing angle can alter the derived speed. In gas-poor systems, researchers may have only a limited number of stellar motions to study, even when a core is present. Dark matter physics may not be the only cause. Ordinary matter can reshape a halo. When gas gathers near the center of a young galaxy and forms stars, supernova explosions can drive some of that gas outward. If this cycle happens repeatedly, the central gravitational field changes again and again. Dark matter particles passing through the region can gain energy from those fluctuations and move onto wider orbits. A sharp central cusp may gradually become a broader core. The result depends on how quickly stars form, how much gas is moved, how often the cycle repeats, and how strongly the galaxy holds its material. A galaxy with too few stars may not produce enough energy to alter the halo. The smallest halos raise another question. Computer simulations predict that a large galaxy, like the Milky Way, should contain many dark matter subhalos. Yet the number of known luminous satellite galaxies was once far smaller than the number of predicted structures. This became known as the missing satellites problem. The gap has narrowed as surveys have discovered many faint dwarf galaxies, some containing only a modest population of stars, and not every dark halo is expected to become luminous. After the first stars and galaxies ionized much of the gas between them, ultraviolet radiation made it harder for the smallest halos to collect and cool that gas. Supernovae could remove what remained. Many low-mass halos may therefore exist with few stars or none at all. A dark halo without stars would not appear in an ordinary galaxy count. Tidal forces add another layer. A dwarf orbiting the Milky Way can lose stars and dark matter, and some satellites are disrupted completely. The population seen today reflects formation, orbital history, and detection limits, not merely the original number of subhalos. A related puzzle was given the name too big to fail. Some simulated subhalos seem too massive and dense to have avoided forming visible dwarf galaxies, yet no obvious observed satellites matched them. Improved modeling of the Milky Way's mass, the effects of its disk, tidal stripping, and stellar feedback has reduced parts of this tension, though questions remain. These small-scale problems are not simple verdicts against cold dark matter. They are places where the nature of dark matter, the behavior of gas and stars, and the limits of measurement become difficult to separate. They also create room for other dark matter models. Warm dark matter would have moved more rapidly in the early universe than cold dark matter. That motion could erase some of the smallest initial structures, reducing the number of low-mass halos. But if the particles are too warm, they also erase structures that observations show must exist. The allowed range is therefore constrained by the abundance of small galaxies and by patterns in gas seen along the paths to distant quasars. Self-interacting dark matter offers a different change. Instead of passing through itself without contact, dark matter particles might scatter from one another occasionally. In the dense center of a halo, those collisions could redistribute energy and produce a core. The interactions would need to be strong enough to affect dwarf galaxies, while remaining consistent with the shapes of larger halos and with colliding galaxy clusters. Ultralight dark matter explores another limit. If the particles are light enough, their wave-like nature could become important across galactic distances. Interference and an effective pressure could smooth the smallest structures and alter halo centers. This possibility is tested through galaxies, gravitational lensing, and the fine structure of intergalactic hydrogen. Each model changes the invisible architecture in its own way. Cold dark matter preserves abundant small structure. Warm dark matter removes part of it. Self-interactions rearrange the centers of halos. Ultralight fields introduce wave patterns at scales where ordinary particles would appear smooth. Future observations can search for these differences in stellar streams, faint satellites, but strongly lensed background objects, and the internal motions of dwarf galaxies. A gap in a stellar stream might reveal a dark subhalo passing nearby. Small distortions in a gravitational lens could expose mass with no stars. More complete surveys may discover satellites too dim for earlier instruments. The work belongs to a long generational thread. Newton described one regime of gravity. Einstein widened it. Later astronomers carried those laws into galaxies and found a discrepancy. Today, researchers test unseen particles, revise dynamics, galaxy formation, and combinations not yet complete. No serious option is protected from measurement. A particle model must explain galaxies, clusters, lensing, the early universe, and laboratory limits. A theory of modified gravity must do the same without adding hidden mass whenever the fit becomes difficult. The standard model remains standard because it connects the widest range of evidence with the fewest changes, not because every detail has been resolved. At the smaller scales, the universe becomes a more exacting laboratory. A dwarf galaxy with only a thin scattering of stars may carry information about particle collisions, ancient radiation, supernova outflows, and the law of gravity itself. The faintest systems can place the strongest pressure on an idea, and in their sparse motions, the invisible framework is asked to reveal not only where it is, but how it behaves. The invisible architecture becomes clearer when distance is added to the map. A flat image can show where galaxies appear on the sky, but it compresses billions of light years into a single surface. A nearby group may seem to overlap a remote cluster, even though the two are separated by most of cosmic history. To recover the third dimension, astronomers measure how much the universe has stretched the light from each galaxy during its journey to Earth. This stretching is called redshift. As space expands, the wavelength of traveling light grows with it. Spectral lines produced by familiar atoms shift toward longer wavelengths, and the size of that shift helps place a galaxy along the line of The method does not provide a simple tape measure distance in every case. It depends on the expansion history of the universe and on the galaxy's own motion. But across large surveys, it allows millions of luminous points to be arranged into a three-dimensional landscape. Filaments emerge from what first looked like scattered dots. Dense knots mark clusters and groups. Long chains of galaxies extend between them. Broad regions contain comparatively little light. The pattern resembles the cosmic web predicted by simulations, but the map is still a map of galaxies. Dark matter remains the deeper layer, inferred from how those galaxies gather and how the light behind them is bent. Weak gravitational lensing helps connect the visible traces to the hidden mass. Every distant galaxy has its own shape. Some are nearly round. Others are narrow, irregular, or tilted at any angle. Between those galaxies and Earth lies a changing distribution of matter. Its gravity alters the paths of their light by a very small amount, stretching many images along related directions. For one galaxy, the distortion is almost impossible to separate from its natural form. No observer knows exactly what that particular object would have looked like without the intervening mass. But when the shapes of many galaxies are compared, the random orientations begin to average away. A faint shared pattern remains. That pattern is called cosmic shear. It is usually far too subtle to notice by looking at an astronomical photograph. It must be extracted from large populations with careful statistics. The telescope's optics can introduce distortions of their own. Earth's atmosphere can blur and shift ground-based images. Detector behavior, image processing, uncertain galaxy distances, and the tendency of nearby galaxies to align with the same environment can all imitate or alter part of the signal. The measurement, therefore, depends on precision in places that seem almost invisible themselves. Stars within each image help researchers model the telescope's point spread pattern. Repeated observations reveal changes in the atmosphere and instrument. Galaxies are grouped by approximate distance so that the lensing effect can be studied at different depths. Independent analysis methods are compared, and simulated images are used to test whether a pipeline can recover a known signal without creating one. Once these corrections are made, weak lensing offers something unusually direct. It responds to total gravitating matter along the path of the light. A region does not need to contain bright stars or hot gas to leave a mark. If enough mass is present, background galaxies carry a small record of it in their apparent shapes. By dividing those background galaxies into distance layers, astronomers can perform a kind of gravitational tomography. A nearby concentration of matter bends the light from every galaxy behind it. A more distant concentration affects only sources farther away. Comparing the shear pattern across several redshift ranges allows the mass distribution to be reconstructed not only across the sky, but through portions of cosmic time. The result is not a sharp photograph of individual particles. It is a statistical field, more like a weather map than a landscape painting. Some regions show greater projected mass, others show less. Broad filaments, cluster halos, and underdense areas emerge after the signals of many faint galaxies are combined. The deeper purpose is to measure how structure grew. The early universe provides an initial pattern through the cosmic microwave background. Later surveys reveal how strongly matter had gathered after 1 billion years, 5 billion years, or 10 billion years of gravitational evolution. A dark matter model must connect those stages. It must begin with the small early variations and produce the amount of clustering observed at each later time. This is where the hidden architecture meets the expansion of the universe. Gravity encourages structure to grow. Cosmic expansion increases the separation between regions. Dark energy, whatever its physical nature, is associated with the accelerated expansion measured in the later universe, and changes the rate at which matter can continue gathering on the largest scales. By tracing both geometry and growth, surveys test dark matter, dark energy, and gravity together. Several modern observatories approach this problem from complementary directions. The European Space Agency's Euclid telescope observes from space, where there is no atmosphere to blur the shapes of distant galaxies. Its wide surveys designed to measure weak lensings and galaxy clustering across more than a third of the sky, following structure through roughly 10 billion years of cosmic history. Near-infrared measurements help estimate distances for galaxies whose light has been stretched far beyond its original visible wavelengths. On Earth, the Vera C. Rubin Observatory repeatedly scans the southern sky with an extremely wide field of view. Its long survey is designed to build a time-lapse record, while also collecting an immense population of galaxies for weak lensing studies. Repetition matters. Many exposures can be combined to reveal faint objects, while changes in the atmosphere and instrument can be modeled across time. Spectroscopic projects add a different kind of depth. The dark energy spectroscopic instrument separates the light of many galaxies and quasars into spectra, measuring redshifts with greater precision than broad color imaging alone can usually provide. Its three-dimensional maps show how luminous matter is clustered and how that clustering changes with distance and time. These instruments do not all observe the same thing in the same way. Imaging surveys provide shapes, colors, and enormous numbers of galaxies. Spectroscopy provides more precise positions along the line of sight for selected objects. The cosmic microwave background supplies an early reference surface. Combining them can reduce uncertainty and expose errors that might remain hidden inside one method. A lensing map can be compared with a galaxy map to learn how faithfully galaxies trace the underlying matter. Galaxy motions can reveal how quickly structures are growing. The bending of the microwave background by intervening mass offers another integrated map of matter across a much longer path. When these observations agree, the allowed description of the dark sector becomes narrower. When they do not agree, the first task is not to announce new physics. It is to ask whether the samples, calibrations, distance estimates, or theoretical assumptions differ. Modern cosmology often works near the edge, where small systematic errors can resemble important discoveries. Confidence grows through repetition, independent instruments, and measurements that depend on different physical effects. There is a quiet discipline in surveying the sky this way. A single dramatic galaxy may be beautiful, but it cannot reveal cosmic shear by itself. The signal appears only after millions of modest images are treated as parts of one experiment. Each galaxy contributes a shape, a color, a brightness, and an uncertain distance. Most contribute almost nothing that could be recognized alone. Together they become a gravitational screen stretched across the universe. Light from remote galaxies leaves them at different times and travels through different regions. Along the way, it passes halos, filaments, groups, and comparatively empty spaces. Its path changes by an angle too small for the traveler to notice. After billions of years, that change reaches a detector as a slight alteration in an image only a few pixels wide. From those alterations, astronomers rebuild part of the terrain the light crossed. The process reverses the ordinary relationship between light and sight. Usually, light shows the object that produced or reflected it. Here, the distant galaxy is both the object and the measuring tool. Its image carries information about matter that lies elsewhere, between source and observer. The web is read through borrowed light. As the maps grow wider and deeper, they will test whether dark matter remains smooth on large scales and clumpy on small ones, whether structure grew at the expected rate, and whether gravity behaves consistently across cosmic time. They may not identify a particle, but they can define the architecture any successful particle or theory must build. The unseen universe is not approached from one direction. It is measured through motion, heat, lensing, clustering, and the long stretch of expanding space. And every new layer of the map turns absence into geometry. The search becomes more intimate when the scale returns to the Milky Way. Dark matter is not thought to be gathered only around distant galaxies. The same kind of halo, inferred elsewhere, should surround our own, extending far beyond the bright disk and enclosing the Sun within its broad gravitational field. We do not look toward that halo. From the outside, we move inside it. This changes the problem. From within a galaxy, the halo cannot be photographed as a complete shape. Its presence must be reconstructed from the motions of stars, satellite galaxies, globular clusters, and thin stellar streams. Follows a path through the combined gravity of visible matter and whatever else surrounds the Milky Way. Stellar streams are among the most delicate tracers. A globular cluster or small companion galaxy can be pulled apart by the Milky Way's tides. Its stars do not scatter at random. They are stretched into long ribbons that continue along related orbits, sometimes wrapping across large portions of the sky. Because the stars began with similar motions, the stream preserves a narrow record of the gravitational field through which it has traveled. In a perfectly smooth halo, that ribbon would develop in one way. But if a compact concentration of dark matter passed nearby, its gravity could disturb the stream. Some stars might be accelerated, others delayed, leaving a gap, a bend, or a change in density. The intruder would not need to contain any stars of its own. This is one route toward finding dark subhalos. The standard cold dark matter picture predicts many smaller concentrations nested within larger halos. Some may host faint dwarf galaxies. Others may have lost their gas or never formed many stars. A stellar stream can respond to both kinds because gravity does not require a luminous marker. Rubin Observatory is expected to discover and measure many such streams, allowing researchers to search for the traces of past encounters with unseen structure. The evidence will not be a simple row of missing stars. A stream may contain gaps left by the Milky Way's central bar, spiral structure, giant molecular clouds, or the remnants of ordinary satellite interactions. The orbit must be modeled. The ages and motions of the stars must be measured. Researchers must ask whether a feature remained stable long enough to preserve the passage of a dark object. The work resembles reading a line that has been folded, stretched, and carried through changing terrain. Dwarf galaxies provide another local test. Some of the faint companions of the Milky Way contain relatively few stars, yet the motions of those stars suggest deep gravitational wells because they have little gas and low rates of recent star formation. They can be cleaner environments for studying dark matter than active galaxy with complex disks. They are also useful targets for indirect detection. If dark matter particles can annihilate with one another, or if they can decay over immense timescales, the process might produce familiar particles, including gamma rays. Dwarf spheroidal galaxies are attractive places to search because they appear rich in dark matter, while containing few ordinary sources capable of generating high-energy radiation. NASA's Fermi Gamma Ray Space Telescope has examined dwarf galaxies, the galactic center, and the broader gamma-ray sky for such signatures. No signal has yet established the identity of dark matter. The galactic center is particularly difficult because pulsars, cosmic rays, gas, and other energetic sources can create overlapping emission. A pattern that resembles a dark matter model must also survive comparison with quieter targets. This is why one bright excess is not enough. A true indirect signal should have a consistent spectrum, spatial distribution, and intensity across environments. It should fit the amount of dark matter in from gravity. It should not disappear when ordinary astrophysical backgrounds are modeled more carefully, and ideally, it should agree with laboratory searches for a particle with compatible properties. The same standard applies underground. A cluster of detector events becomes persuasive only when its energy distribution, timing, and response across different target materials match a coherent particle model. A seasonal variation alone would not settle the question. A single instrument could contain an unrecognized background. Independent experiments would need to see related behavior. At particle accelerators, the strategy changes again. Protons collide at high energy, producing showers of known particles recorded by layers of detectors. If an unseen particle were created and escaped without interacting, it would carry momentum away. Physicists could infer the imbalance by adding the visible products and finding that they do not balance. Missing momentum does not automatically mean dark matter. Neutrinos leave detectors in the same general way, and imperfect measurements can create false imbalances. A candidate process must exceed known backgrounds and fit a detailed pattern of associated particles. Even then, the new particle would need to be stable and abundant enough to explain the dark matter measured in the universe. CERN describes these searches as a route toward clues, not a direct guarantee that a missing energy event identifies the cosmic substance. This distinction matters because production and identity are not the same. A collider might reveal a new invisible particle that decays too quickly to fill galactic halos. An underground detector might respond to a particle that forms only a fraction of dark matter. An astronomical signal might arise from a hidden interaction without revealing the full particle family behind it. The dark sector may be simple, but nature is not required to make it so. Ordinary matter contains several families of particles, multiple forces, stable atoms, unstable nuclei, and complex structures. It would be an assumption, not a discovery, to insist that all unseen mass must be one particle with one interaction. The eventual explanation could involve several components, whose combined gravity produces the architecture already mapped. This possibility is one reason different experiments remain necessary. Stellar streams test the clumpiness of the halo. Dwarf galaxies test mass in small gravitational systems. Gamma-ray telescopes search for products of annihilation or decay. Underground instruments wait for rare collisions with atoms. Accelerators attempt to create new, invisible states. Cosmological surveys measure how the hidden component-shaped structure across time. Each method approaches a different surface of the same unknown. There is a generational patience in that arrangement. One group builds a detector beneath rock. Another measures faint galaxies from orbit. Another follows streams across the Milky Way. The researchers may never see the final synthesis themselves, yet their limits and maps become part of it. Scientific progress often looks like this from within its own era. Not a single door opening, but several walls becoming thinner. A null result removes one class of interactions. A cleaner map narrows the allowed halo structure. A dwarf galaxy places a limit on annihilation. A collider rules out part of a model. None of these acts alone can name the hidden substance, but together they reduce the number of worlds in which it can exist. And if a discovery arrives, it will likely be recognized through agreement. A particle mass, inferred in one experiment, may predict a recoil energy in another. Its interaction strength may imply a gamma-ray signal that either appears or remains below a measurable limit. Simulations using those properties may reproduce the abundance of small halos and the shapes of galactic centers. Lensing maps may reveal the same large-scale clustering. The invisible architecture would then become connected to a physical ingredient. Until that happens, dark matter occupies a rare scientific position. Its gravitational role is woven deeply into the working model of the universe, while its material identity remains open. The evidence is strong enough to guide observatories and simulations, yet incomplete enough to support several competing possibilities. We live inside that uncertainty. The solar system crosses the Milky Way's halo. The galaxy travels within the local web. Light from distant objects passes through layers of unseen mass before reaching our instruments. The search is not directed toward one remote place where the answer is hidden. It surrounds every observation, and somewhere between the motion of a faint star and the silence of a protected detector, the architecture may finally disclose what carries its weight. The architecture remains invisible, but it is no longer without shape. Across the universe, stars move inside galaxies whose gravity reaches beyond their light. Galaxies travel through clusters held by more mass than their luminous contents can provide. Distant images bend around concentrations that telescopes cannot photograph directly. On the largest scales, filaments gather around broad voids, preserving the slow growth of structure from the first small differences in density. These clues do not all depend on the same instrument. Some come from radio waves emitted by hydrogen. Some come from X-rays released by hot gas. Others appear in the stretched shapes of remote galaxies, the motions of stars, the pattern of relic radiation, or the positions of millions of luminous systems across deep space. Their agreement is why dark matter occupies such a central place in modern cosmology. It is not accepted because a single observation demanded it. It is used because one hidden component can connect many observations that would otherwise remain separate. The same broad idea helps explain the rotation of galaxies, the binding of clusters, the bending of light, and the formation of the cosmic web, yet the name still marks an absence. Dark matter tells us how the missing component behaves gravitationally. It does not tell us what the component is. The word matter may eventually prove accurate in a familiar particle sense, or it may refer to field, several particles, compact objects formed in the early universe, or some description that has not yet become part of physics. Science can work with that uncertainty without treating it as failure. A model may be powerful before every ingredient is understood. Long before the interior of the sun was explained, its gravity could be measured and its path across the sky predicted. Long before atoms were imaged or their components identified, their effects were present in chemistry. The unknown nature of dark matter does not erase the gravitational evidence. It defines the next boundary of the investigation. That boundary is being approached from several directions at once. Astronomical surveys continue to map how matter is distributed across time. Measurements of dwarf galaxies and stellar streams examine the smallest structures that dark matter may form. Colliding clusters test whether it passes through itself and ordinary matter without much resistance. Underground experiments search for faint transfers of energy. Resonant cavities listen for fields that might convert into light. Particle accelerators look for invisible products carrying momentum away. Each method is sensitive to a different possibility. A particle too light for one detector may be accessible to another. A form of dark matter that never touches atomic nuclei might still alter the abundance of small galaxies. A hidden component that interacts with itself could leave its signature in the centers of halos. A revised theory of gravity would need to reproduce the same broad structure without relying on an unseen population of particles. There is no guarantee that the final answer will resemble the most familiar candidates. WHIMPs once occupied much of the search landscape, partly because they arose naturally in extensions of particle physics and could have been produced in the early universe with an appropriate abundance. Their continued absence in direct searches has narrowed many possibilities, but it has also encouraged experiments to look toward lower masses, weaker interactions, and different detection methods. Axions began as a possible solution to a separate problem in nuclear physics, then became dark matter candidates of their own. Ultralight, fields, sterile neutrinos, hidden photons, self-interacting particles, and primordial black holes each occupy other regions of the map. The map is wide because the evidence for gravity does not specify the microscopic cause. In that sense, dark matter is both well-established and deeply unsettled. Its influence is measured, its identity is not. Those two statements can remain together without contradiction. The future of the search may depend less on one dramatic instrument than on the joining of many quiet measurements. A small distortion in a lensed galaxy may constrain the mass of a subhalo. A gap in a stellar stream may reveal an object with no stars. A laboratory may record a rare event with an energy pattern that points toward a particular particle. Another experiment, built from a different material, may see the same interaction from another angle. Only then would the pieces begin to settle into a common form. A genuine discovery would need to explain more than a detector signal. It would need to fit the architecture already written across the universe. Its properties would have to permit galaxies to form, clusters to grow, filaments to emerge, and the early density pattern to develop into the cosmos observed today. The universe has already performed the longest experiment. It has allowed the hidden component to act for billions of years. Every halo, cluster, and filament contains the accumulated result. This is why astronomical observation will remain part of the answer, even if the decisive clue appears underground. A particle created in a detector must still be connected to the mass surrounding galaxies. A new law of gravity must still reproduce the relic radiation and the cosmic web. the local and cosmic evidence must eventually describe the same reality. Until then, the invisible architecture can be understood without being imagined as a dark version of familiar matter. It has no known color, no known surface, no confirmed temperature in the ordinary sense. It does not form the bright disks that telescopes record, and it does not gather into the dense atomic structures that make planets, oceans, or bodies. Its presence is expressed through arrangement. It determines which paths remain bound. It deepens the regions where gas can collect. It helps preserve small differences until they become galaxies. It guides clusters toward the intersections of filaments and leaves voids with fewer luminous systems. The visible universe is not placed on top of this framework like decoration on a rigid frame. Ordinary and dark matter have evolved together through gravity. Gas fell into halos, cooled, and formed stars. Stars changed the gas through radiation, winds, and explosions. Galaxies merged and their halos merged around them. The luminous and invisible components shaped one another's histories, even though only one produced the light reaching our eyes. The relationship is still unfolding. Far in the future, galaxies within bound groups will continue to merge. More distant regions will recede as cosmic expansion continues. The large-scale pattern will change in what remains connected and what passes beyond reach. Dark matter will remain part of that evolution unless a deeper description reveals that we have misunderstood the architecture itself. For now, the best view is neither certainty nor doubt alone. It is a carefully measured landscape. Galactic rotation shows one contour, cluster motion shows another. Gravitational lensing fills in regions between them. The cosmic microwave background provides an early outline. Galaxy surveys trace what grew from it. Laboratory experiments search for the substance beneath the map. The search continues because the map is coherent enough to trust and incomplete enough to question. And somewhere beyond the last visible star in a galaxy, the same hidden gravity continues outward. It passes through regions where the glow has become too faint to follow. It surrounds the disk, joins the larger filament, and becomes part of a network extending far beyond any single system. The light reveals where matter has gathered. The motion reveals that more is there. The hidden framework keeps carrying the light.